seismic exploration methods to coalfield exploration problems. And in a series of, we have three different events like talks, then panel discussions and business meetings. So in this, we will see that how seismic techniques, what NGRI and other participants have modified and developed, how it can be made useful for coalfield exploration problems. And at the same time, we would also like to see that if coal fields in India and the depleted oil and gas fields in India are suitable for CO2 sequestration. So that is one business meeting we have. So I request our director, Dr. V.M. Tiwari, to give his opening remarks and the welcome address. Over to you, sir.
Thank you, Nimita. Please switch off your mic so that we can reduce echo. Namaskar and very good afternoon to everyone, all panelists, as well as participants, colleagues from industry, students, and future industry. We all are aware that post-pandemic, there had been a lot of discussion. How can we meet the requirement of our countries? And for any society, energy, environment remain focus area for future sustainability. And therefore, there was a discussion amongst the science ministries to understand how science and technology can help at the time when India calls for Atmanirbhar Bharat. In this context, Honorable Minister for Science and Technology, Dr. Jiten Singh Ji, has advised when India celebrates 75 years of its independence, let us have 75 events commemorating the success of the science, the stories of the science, and connect with the industry in order with the two objectives. One, that bring industry to the fold to upscale the technologies and the technological interventions which are adopted by the scientists in the country. And other, that if industry is facing issues, how the scientific problem through academia and science industry connect can solve those problems. So with these two major objectives of having iConnect, Industry Connect with Science, 75 events being organized by Ministry of Science and Technology, Ministry of Earth Sciences, and other allied science departments and ministries. I'm very pleased that we have panelist speakers today with all the stakeholders from industry, people from academia, and also from scientific departments and ministries. To discuss the problem, which we are often find difficult to address, is how can we hire environmentally friendly environment which has the less environmental impact, or we have the technology which can reduce or meet the India's commitment of the 2070 zero carbon, and also meet the requirement of the country. We all know that among several resources, coal and coal-bed methane, particularly if we see the status globally, among top 5 countries, India is one among the having resource potential of the coal-bed methane. Therefore, there is a need to understand how much do we know about it And once we know how best we can exploit these resources, which is economically possible and environmental friendly. In this respect, CSIR and GRI having a large number of scientists working over decades, develop expertise and experiences in seismic methods of utilizing technologies for exploration of coal and coal-based methanes, even very thin layers of the coal seams can now be detected using the kind of technologies which we have from source to the modeling like with full waveform inversion. In this respect, the nodal, Dr. Nimisha Vedanti and other colleagues came with the proposal to have this event, and I congratulate all of them for such a thoughtful initiative for bringing people from the different forum and also planning for a theme which is so relevant in the today's world of science and technology and sustainable living requirements. I am also very pleased to welcome all of you for today's meeting, and I wish that this initiative does not remain only an initiative for our discussion, but pave the path or working together towards the mission for which I connect 75 I events which are organized by Ministry of Science and Technology and Earth Sciences to address the issues of the country uh, at large and also the connect between the scientists and industries and the other stakeholders and also generate the new possibilities of developing the new industry, new startups, and new entrepreneurship. With this, I once again take this opportunity to welcome all of you for this event and wish very best for the discussion. I look forward to learn from your deliberations so that we can take the final discussion points, final recommendations of this meeting to action. Thank you very much. Jai Hind.
Thank you, sir. Sir, before I start this event, we have a representative from Telangana and Andhra Pradesh, Vicky. Mr. Shastri is here, so I welcome him. He is sitting here in the audience. And then after the panel discussion, we'll request him to give his closing remarks. So he just joined in the middle, so I thought of welcoming him here. So thank you, sir, for joining us. So,
Thank you, sir.
yes, sir.
Thank you, sir. Thank you. Pleasure to be here, sir.
So, as I described our session in the beginning, that this is an iConnect event, not a ordinary conference where we make the technical presentations and we'll have a detailed Q&A session and all. So we have instructed all the speakers to stick to the time and complete their presentation, whatever techniques we have developed, we want to share with the industry in 10 minutes. And industry is expected to come up with some of the problems what they are facing in coalfield exploration. So following that, I'll start the presentation sequence, which eventually starts with me. So just give me 1 minute, I'll load my presentation. So basically, the theme of this iConnect event is to take seismic exploration technique to the coalfield exploration problems. So when we talk about the coal field exploration, it is basically we talk about the high resolution data. And this is some of the results I would like to show, that whatever techniques we have developed in our institute and whatever results we have obtained in the real field scenarios, that I will quickly share with you. And then I'll over this to other speakers of the session. So we all are, means all of us are somehow or the other related to the coalfield exploration problems. We all know what type of prospects we are looking for in the coal field. We are looking for the coal which you can see that they are like a bed type of stratified structures in the geological formations. Then we will have some partings which will be either shale parting, some sedimentary formation will be there. So these type of structures generally we look for to map in when we go for a coal field exploration. So the thing looks very simple because generally these coal formations will be hosted in some of the sedimentary formations where there will be a good impedance contrast, because coal generally is a porous rock. It will have a low velocity, low density. So ideally it should give a very good, very beautiful signal in the seismic data. But why it is a problem when such a good acoustic impedance rock we are finding it difficult to map? So the answer lies between that, because of it's not really a big thick formation which we are looking for. There are lot many discontinuities in the coal. We are looking for some small scale fractures, small scale structural discontinuities, and we are also looking for very thin coal seams, like our director has already mentioned that mapping of thin coal seams is a really problem in the coal field mapping. Then mapping of these partings, because if we are going for any prospect evaluation or any reservoir characterization problem, we need to have a clear image of all these beds plus all these discontinuities and all these layers which might be impermeable for any flow. So these are the challenges which generally the coal field exploration people will face. And other problem is that this prospective coal layers are not very deep. Like if it was an hydrocarbon exploration problem, we are fairly deep. So the complexity in the earth with depth, it reduces. So we don't really deal with too much complex overburden in the hydrocarbon exploration problem. But in coal field, we are very much confined to the shallow surface, and then there is a lot of complexity. And especially in the coal fields, the Indian Gondwana coal fields where we have worked, we have seen the targets are shallow, there are patches are inaccessible, there is a lot of attenuation because of multiples, because of loss of energy in the coal layers, and the coal is anisotropic, so we are not really able to map it properly. So overall, it's a complex overburden what we are dealing with, and then we are expected to solve a geophysical problem from an exploitation point of view, not just the structural mapping or mapping of just the stratified layers. So the mining industry expects geophysics uh, to give results which can be used for further extraction and exploitation. So the kind of resolution which is required from the coalfield exploration people is much higher, and the data quality is very poor compared to the hydrocarbon exploration problem. So this is the main challenge what we face when we analyze the seismic data which is acquired in a coal field, that we are required to give accurate model which is 1 meter accuracy, up to 1 meter accuracy we are expected to give in the low signal to noise ratio environment. Now, when we are planning to map these small 1 meter discontinuities or 1 or 2 meter thin coal layers, we are always pushed towards the dominant frequency. That what is the frequency in our seismic data? Is it sufficient to map this type of discontinuities or all? Somehow I find it little difficult that when people talk about the high resolution, they always talk about the high frequency. So I want to make it clear that high frequency doesn't always mean the high resolution. So when I'm talking about the high resolution seismic data, it doesn't necessarily mean that I'm acquiring the data at very high frequency. What we need a full bandwidth, a broad bandwidth data to enhance the resolution of the seismic data. So to see synthetically that for a given field, how much resolution, how much frequency content do we really need? And this my students have done this synthetic modeling. And here you can see a small fault and these thin layers. These are just at the 80 Hertz frequency. Those are resolved, and we are able to image this type of cases even with 80 Hertz. So why do we have to go much beyond that? Of course, in the ideal scenario, we can, but sometimes demand is very high. Even these are maybe 5 to 10 meter thin layers which can be resolved. But if we have to go below 2 meters or so, probably we'll have to increase the bandwidth. But again, there is always an attenuation problem happening in the cold field. Even if we use very high frequency sources, what we have seen practically, it doesn't really seem to help. And what we found that if we are dealing a single seam exploration problem, then if we enhancing the frequency content of the data will be really helpful, because our detection capability will definitely increase. But our problem is we have multiple layers of cold seams, and then our target will be at certain depth, where in overburden we will have several thin seams. So for us, the only high frequency component is not important. What we need is a full bandwidth data that will have a low frequency and high frequency both. So keeping in all these things in mind, we have developed certain flows, certain algorithms to handle these cold field exploration problems. So some of these, because what I will call it is a process development rather than a technology development, because what we are using is a combination of several techniques. It's not really one single technique what we are going to use for cold field exploration. So we started with the acquisition. We have started looking into the seismic sources, whether we can go, how low we can go in this frequencies. So we found that we can go up to 5 to 7 hertz in the frequency, which is shown here. So we have enhanced our bandwidth in the lower frequency bandwidth side. We have worked on the modifying the conventional processing algorithm to fit into the cold field exploration problem, to compensate the attenuation happening in the cold layers by using the Q compensation migration. Then we have also started using a module surface wave modeling algorithm, which gets rid of the ground roll, because ground roll is the main noise which is corrupting our entire data in the exploration. So these techniques are working very fine. In addition to that, we have recently started working on the joint reflection and reflection tomography. Till now, we had been using only the reflection data for to map the coal seams, but in the coal fields, we always face this velocity inversion problem, because all these sand shell strata will have a higher velocity and coal layers will have a lower velocity. So the velocity inversion problem is not really dealt nicely with the conventional algorithms. So we have started working on this joint reflection tomography, which will generate a more reasonable velocity model. These things in the subsequent sections and the B2B meeting, my other colleagues will explain in more detail. So I'll just quickly scroll through this. In addition to these processing workflows, we have developed certain algorithms. One is to enhance the resolution by using the stochastic inversion algorithm. This is one in-house developed algorithm in which we have, right now we have shown only on a 2D data, in which we are able to map a 2-meter thin coal seam also with this algorithm. And it was tested on a 2D line of a Mahanadi basin data. You can see a picture here. So it is working fine. Now we are in the process of making a software out of that. Second algorithm what we are working on is the wavelet decomposition technique. So we all know that in the coal field we'll have several different coal layers above our target coal layer. So what we are trying to do is to develop a scheme which can get rid of the all other overlying coal seams, and we get the reflections from the target coal seam, which can be interpreted very easily for any structural discontinuities or any further characterization. So this algorithm is under process of development. One more algorithm what we had been working on is till now the stochastic inversion what I have used here. Here we need at least one sonic well to run this algorithm, because some information it will take from the well to enhance the frequency bandwidth of the data. But in case of virgin area where we do not have any well and the first time this exploration program is going on, we need to have some technology which doesn't need the well data. So we are developing a high resolution spectral bandwidth extension algorithm, and we have already developed it and used it on a public domain data set, and you can see the resolution of the beds has increased, and the spectrum also you can see that in the lower frequency side also it is increased, and in the higher frequency side also it is increased. So this technique we are finding it very useful on the good quality data set, but somehow we are still struggling to work on this to fit it to the coal exploration when coal data. Now, in addition to those advanced developments, we had been working on the conventional problems like mapping fault in the coal seams, mapping basement, mapping of floor and roof contour map, or the formation thickness map for different formations, preparing a geomodel. So these things we have developed the capability to cater to the commercial aspect of any exploration block. We are also looking into that if we are able to quantify the gas content in the seams by looking into impedance data. This is just a test case that in which we can see that in the top seam we have low impedance and high impedance anomalies, but in the base of that seam we don't have the low impedance, which could be an indication of presence of gas in the coal seam. So this type of processes we had been working on. So to meet these coalfield exploration problems, we have enhanced our acquisition, processing, interpretation, and the well logging capabilities. So we have also run one experiment to do a multi-vibrator survey. Right now, I do not have the results to show that. But to take care of attenuation up to a certain extent, we are capable of running a multi-vibrator survey. And we have seen that with our this Hemi 50,000 pound capacity vibrator, we are able to reach up to 3 kilometer depth with the P-wave source. We are also capable of running the multi-component data in the coal field, and recently we have completed one experiment in partnership with SR, where we have 25 line kilometer data we have acquired in multi-component data we have acquired. So these capabilities we have enhanced to this multi-component data is really going to help us in determining the lithology, because we find it very difficult to discriminate between the sand shell lithology, especially for the deeper formations in the seismic data. So this is really going to help us. So this is how we have enhanced our existing capabilities at the shallow seismic group at NGRI to meet the coalfield exploration problems. So thank you. So generally, we are not taking question answers immediately here. So what we have planned is if we have sufficient time in the end of these talks, we will have a Q&A. Otherwise, we will direct all this Q&A to the business meeting. So and now I request Dr. Jyotirmay Malik to make his presentation. I'll quickly give his introduction. Dr. Jyotirmay Malik is visible on the screen. He is associate professor at iCER Bhopal, and he has over a decade of experience for working with the shell in oil and gas industry. And he has been working on these CBM problems in Australia for quite long time. So we have requested him to make a presentation on the coal permeability estimations. So Jyotirmay, it's over to you.
Thank you, Dr. Nimisha. Am I clearly audible, visible, and my slides are visible?
Your slides are visible. You go to presentation mode.
Yes, now I am in the presentation mode as well. Are my slides visible in presentation mode?
Yes, yes.
Okay. So thank you very much for inviting me to speak at this forum. And what I'm going to do here is to speak about the coal permeability modeling using seismic attributes, the work me and my students are doing here for last 2-3 years. Some of the works are very preliminary, so has yet to be mature. So yeah, let's go ahead with the presentation. Somehow my okay. So why it is important to understand the permeability system of coal, and why it is very important to model them. So unlike conventional gas or oil reservoir, coal is very different. So what happens, as we all know, the coal seam gas essentially is not a free gas. It is generally absorbed in the coal matrix. And the coal matrix has very little, almost insignificant, close to zero permeability. So all the permeability is attributed by the fractured system that is inherent in the coal. We all know coal generally has a naturally occurring fractured system, which we call as clades. They are generally of two types, face clades and butt clades. So if we wish to understand the permeability system of coal, we have to understand its fractured system, and that is what we are focusing on. So why this permeability would be interesting? Simply because, of course, to you know dewater coal, because dewatering coal is the first step to extract coal bed methane, because that is what creates drawdown, the pressure drop between the coal matrix and the coal fracture system, and the gas comes out. And of course, you have to know about the permeability system if you wish to use coal seam as sink for CO2 sequestration. So understanding permeability is absolutely crucial, and predicting permeability in a pre-drill scenario is also very crucial. And we are mostly looking at the work that I am going to show you today is around the Raniganj Basin. So let's go ahead. So how generally permeability is modeled, or permeability modeling is approached in industry and in academia. Let me talk about the industry first, and I hope my industry partner will agree with me that generally in coal bed methane, there are lots of wells are actually drilled, and you have some sorts of measurement of coal permeability data. And you can see in the left graph, these red dots represents coal permeability coming from different sources, and you can see the scatter. There is a general trend of decreasing permeability with depth. So as the depth increases, the permeability decreases, but the scatter is really, really high. And what is generally done, you have a base case model for permeability from the data, you have a high case model for permeability, and you have a low case model for permeability. Now, this is there a question?
Please unmute all of you. Better.
Okay, so there is a lot of scatter in the data, and this is how generally permeability models are achieved in the industry. But what is done in academia, including us, we can look at these different fracture parameters, fracture attributes, we can analyze them, and we can come up with some analytical models. This is a very simple analytical model where permeability is kind of associated with the fracture aperture, and several such permeability models have been achieved, some by our lab as well, and you can calculate permeability. That is one very simplistic way of calculating permeability that is done in the academia. The other way of calculating permeability in academia is adopted by doing something called discrete fracture network model. What you are seeing here is the picture, it's a micro city picture of a very small coal chip. Okay, and you can see here its fracture patterns, and this particular fracture pattern is actually translated into a 3D fracture network model, which we call a discrete fracture network model. And ultimately, this fracture network model would be converted into a permeability model. Now, the problem here is, of course, is the scale. You can see at which scale this permeability model is being developed. Uh, it's really, really small. I mean, it's almost insignificant if you think about the well drainage radius, where the permeability that should matter in terms of exploration or production. Okay. Similarly, analytical models is too simplistic. That has its own problem as well. And the industrial approach, which is currently being taken, has its because the uncertainty is really, really huge. We must find out a way to have a permeability model which is done in a pre-drill scenario and which takes care of all these challenges. Now, if we look at these challenges a bit more seriously, you will find that this is a chart which is provided here, which we actually published. Uh, it shows how permeabilities are different from a pre-drill prediction to what permeability has been found in the field. So this is in the San Juan basin, and you can see this is the permeability that was predicted, the permeability spectrum, and the permeability which is observed in the field. Similarly, you can see this is actually a combination of different basins that we observe in Europe. This is the permeability which is predicted, and this is what has been observed. So the gap is really, really huge. This is for Raniganj coal seam, although this gap is little bit lesser because there have been um, uh, some estimates which have been I don't know what exactly the reason is, but still the gap actually exists, and this is generally attributed, why this permeability gap is attributed to this uncertainty chart. What it means that there are several factors which affects permeability, okay, and which are completely not looked after while a permeability model is generally made. Only the depth and its dependence on permeability is looked after, and all these parameters which affects permeability to a great extent is generally overlooked or not being considered in while developing a model. So what we have done, this is me and my students, we have collected samples from different mines of the Raniganj field, and you can see we have collected samples from underground coal mines, open cast coal mines, so that it represents different depths. Then we have looked at these fracture parameters on a multiple number of samples, hundreds of samples, to characterize and to understand if there is a pattern in this slit system, if there is a pattern in this fracture system. We have looked through hand specimen, optical microscopy, ACM, X-ray microscopy, you name it. We have analyzed lots of samples, and we have created a huge fracture database for Raniganj coal seam. Then we have developed our own analytical model. We have developed our own discrete fracture network model of different areas, did permeability modeling, calibrated our data with the existing data set that is present from the industry, and then of course and published data, of course, and then we have brought in the aspect of seismic to understand permeability sweet spotting. What do I mean by sweet spotting? By sweet spotting, I mean to find out areas which are preferentially with higher permeability than the rest, and I will explain how we essentially do that. So to understand that, let us think of a simple conceptual model. Let us say this inherent fracture system, these cliffs actually provide a background permeability to coal, okay, which generally decreases with depth. Now, if your coal seam is deformed, if there is a fault, if there is a fold, what essentially it does, it develops a second generation of fracture. It develops another generation of fracture which gets superimposed on the existing fracture system and enhances the permeability. These fractures can be found out, these fracture corridors or areas of enhanced fracturing can be found out by analyzing seismic attributes. The most important seismic attribute we are analyzing is curvature. And then you can prepare permeability model with your grid. You can prepare permeability model with your tectonic fractures. You can club them to using a algorithm that we have developed, and you can create a regional permeability model. So here is an example. You can see here, these are some of the seismic lines thanks to NGRI was at our disposal to study. And this is a simple 2D permeability model that was created on one of the seismic lines. And you can see we have done a very detailed interpretation on the seismic lines to map out the coal seams. From there, we have created a semi 3D, I mean, a pseudo 3D mode like a 2D model. And from that model, we have actually you can create a cliff model, cliff permeability model. You can also create a fracture permeability model, and this black line actually represents the cliff permeability model trend. This uh, red line represents the fracture permeability model trend, and how the actual observations are distributed along them, which is pretty good in if you try to judge them. Okay, so that's how you create a integrated permeability model. So you have slit permeability model, normalized joint permeability model, the model which is created from tectonic fractures, and then you put together a simple permeability model that kind of combines both of them, including the depth trend and all the uncertainties that I have talked about. Now, we have not stopped there. We have also started working on a very small scale 3D model. As you can see that this data is really dispersed. So if we have more data, of course, we will be able to create a better model. So now we are only focusing on this small sector because of the density of these seismic lines. From there, we have created a 3D geocellular model. And this is a geocellular structural model with all the faults and stuffs in it. And then we have created a cliff permeability model, a joint permeability model, and put them together to create a model which actually combines both of them. Now, the interesting part is you can see in this model there are places which are with hotter color, and there are places which are with more milder color, more colder color. So these hotter color areas actually represents areas with permeability sweet spot. These are the areas where you will, if you drill, our prediction is you will find much better permeability than areas which are here. Okay, so with that note, if you think about it, and this is where our combined permeability actually lies, and these are the data that have been essentially found. These are the data that comes from industry and published literature. Okay, now what is the advantage of this technique? And this is where I think we wish to understand how industry thinks about it. Currently, the practice in the industry in case of coal bed methane is to do grid drilling. You have a grid, you would divide the area into different grids and drill number of wells. Okay, without exactly, I mean, not always constraining to understand whether this particular area is good or this particular area is bad in terms of permeability or gas content and so on and so forth. Okay, now if we go for a sweet spotting scheme, okay, then you might be able to reduce the number of wells. You might like to avoid the areas which are less permeable. Similarly, you can create your gas content sweet spot map, maybe overlay the two, and understand or actually decide on what are the areas you wish to drill and what are the areas you wish to avoid. I think that would minimize cost, that would minimize risk associated with grid selection. There is these are some very initial results to along which we are actually approaching. Even we have more data, and our model and hence our model will be more constrained, and we will be able to use seismic technology and its attributes to contribute towards permeability sweet spotting and permeability modeling to a greater extent. So with that, I will stop my presentation. I hope I was on time, and I wish to thank the organizer once more. Thank you very much.
You are on mute.
Am I audible?
Yes.
Okay. So thank you, Jyotirmay, and I'm sure audience must be having a lot of questions for you, but we'll take later during the panel and the B2B meeting. So now I request S. Naresh Kumar, Senior Manager of CMPDI Exploration Wing, to make his presentation. Naresh, you can share your slides.
Hope my slides are visible.
Yes, Naresh, visible.
Shall I continue?
Yes, please. Naresh, you have 10 minutes time to make your
that's fine.
presentation. Okay.
Okay. Respected dignitaries, good afternoon, everybody. First of all, I would like to thank NGRI for organizing such a great event and bringing industries and research organizations on one platform to discuss various problems and solutions in the coal exploration sector. Today, I'm going to present application of seismic survey to address different challenges in coal exploration. So basically, I'm going to discuss main challenges we are facing, which has already been discussed by Dr. Nimisha Vedanti. But I have some other issues to be discussed. So we have a major three major issues that needs to be addressed. Um, the conventionally in coal exploration is being done through core drilling, and number of borehole per square kilometer ranging from 3 to 15 depending upon the stages of exploration. For example, if it is a G1 stage of exploration, it is ranging from 10 to 15 as per previous ISP norms. And this borehole density per square kilometer increases depending upon the complexity of the borehole, geology of the block. In India, as of now, we have 17,394 unblocked area left, which needs to be explored for coal exploration. And CMPDI is having a capability of exploration capability combined with departmental as well as outsourcing is around 12 lakh meters per annum. With this space of exploration, we want to explore this unexplored area. It will take minimum 50 years of time. Exactly. Yes, it is minimum 50 years of time. So now the challenge is, first challenge is how to increase the space of exploration. So CMPDI, to increase the pace of exploration, has CMPDI optimized each and every operation of exploration, ranging from shifting from coring drilling to non-core drilling, and and even hybrid drilling they have used, implementing of this surface geophysical techniques in coal exploration. Earlier, this seismic is used to aid the exploration activity, but not as a mainstream exploration activity. Now, this seismic coupled with 2 to 3 boreholes per square kilometer to enhance the space of exploration, we have adopted that methodology to increase the space of exploration. By doing that, we have reduced the time and cost substantially. You can see this through conventional method. The cost of drilling is around 130 lakhs per square kilometer, and the time required is around 40 working days. The same is if it is with 2D with 2 borehole per square kilometer, the cost reduced by 41% and time reduced by 37%. Same in the case of 3D seismic survey with 2 borehole per square kilometer, the cost reduced by 30% and time is reduced by 50%. Moreover, by this application of seismic for complex geologies has reduced the additional boreholes required for proving the complex structure of the block. So next, I'm going to while implementing this seismic technology in routine exploration, we are facing different statutory norms. Complying with statutory norms become a bit difficult. Why? Because these statutory norms are prepared based on the requirement of oil industry. So major issue what we are facing is with MOF guidelines. So as per this MOF guidelines, which were issued in 2019, 80 boreholes is the maximum permissible limit per square kilometer in a forest area. As you are aware that exploration objectives and requirements of oil industry and coal industry is completely different. be it the depth of investigation, group interval, short interval, and the size of the blocks what we are dealing is completely different. Accordingly, the this requirement will also change. Here, with 80 shots per square kilometer norm, in oil industry, they could easily achieve the substantial fold data. But with this norm, if we are trying to obtain data, hardly we will be achieving 6-fold data, not much. So these norms needs to be revised. For that, we have already requested ministry to increase this 80 shots per square kilometer to at least 250 shots per square kilometer, so that in forest area we could achieve substantially good amount, good quality of data to resolve this. And in addition to that, we are planning for do some R&D through passive seismic with periodic generation of waves at different arrays. We are planning for that. By doing that, at least in these inaccessible forest areas, we can achieve the data through passive seismic and to substantiate this with the non-forest area where we are facing these kind of difficulties. And the challenge 3 is the specific requirements of coal industry. As Dr. Nimisha has already discussed, that in coal industry, the resolution required is very high because of it is a requirement of the planners to plan the open cast mines and underground mines. They need a different requirements. Even they want a resolution of 0.9 meter. And even theoretically, it is difficult. It is not possible to achieve this thin seam delineation and dirt bands, what we call non-coal layers within the thick seams. Identification of those dirt bands is very much essential to accurate determination of coal resource and all, on which the actual economics, mine economics, and mine operation economics depends. And despairing the splitting, merging of the coal seams. These are the requirements which needs to be addressed through different geophysical techniques. And major issue is imaging the coal seams beneath these traps, like Deccan Trap in Maharashtra, Rajmahal Trap in West Bengal region. Imaging the seams below these traps is challenging task, and we need this institutes, academic institutes support for doing R&D in these areas. So, as I've already told you that with our experience and the theoretical aspect, also we have derived this, we could see this resolution, possible resolution with increase of depth. It is to resolve the required thickness of seams, what miners are looking for. However, with seismic in oil industry, where 10 meters of resolution, what they're looking, we could achieve it to 5 meters, even lesser we are trying to achieve. In this resolution issue, we have a further development. Jointly, we have developed an indigenous software jointly by CMPD and Gujarat Energy Resource Management Institute, Germany, Gandhinagar. We have developed a software spectral enhancement for thin seam delineation. This is based on the principle of inverse continuous wavelet transform. By developing this software, we could attain the resolution by another 40 to 50%. That means in shallower, we could achieve resolution of even 2 meters, even less. Deeper, as per this chart, we have further, at least we could achieve the 50% of higher resolution. I would like to show the capability of this software through some case studies. So this is the basic principle what we have followed in developing this software. We are having a seismic trace, and through wavelet transform, this wavelet transform. After doing this wavelet transform, we have obtained this wavelet transform modulus minimum lines, and again we have reconstructed the space. By doing this, we could see this refinement here in the red circles, it could resolution has increased. And here with the green circles, you can say that resolution, better resolution and fine refinement, which was missing in the left side trace, you could see those finer refinements in the reconstructed trace. Here I'm going to show you 4 case studies. Oh, I'm running out of time. Okay, these are the case studies you can see in the left side. This is a conventional output what we get through softwares. And you have on the right side the output of this result, spectral enhancement SPA software result. You can see this how beautifully it has enhanced the spectrum, and through Weltai also it can be seen that very finer seams have been identified that helped in identifying the structures and all. This is another case study where we have seen the similar good kind of results. Here you can see on the left side this parting of the seam is very not much definer, and the right hand side you can see this splitting, parting. These kind of things can be identified very much, and you can see this definition how well the thin seams have been resolved on the right side of this section. And finally, this requirement of as per the mine requirement, this ash moisture content and total organic content, GCV, and all these things are intrabed properties. What we are looking resolution, all these things are intrabed properties, whereas this ash moisture content, total organic content, and GCV, ministry is trusting to derive these values from seismic survey alone, which is a lot of scope of research and development. But we could achieve these things through machine learning using the boreholes and geophysical log data. We could do this, but through seismic alone, it is difficult. So far, we couldn't do that. But integrating, yes, we can do that. So in this area, there is a lot of scope for R&D, and CMD is always welcome any projects in these areas. Thank you for giving me this opportunity. Thank you, one and all.
Thank you, Naresh, for your excellent presentation, and your results really look very impressive. So you can unshare your slide. We'll take questions for you later, Naresh. So anyone from audience, if you want to ask questions, please put them in the chat box. We'll take them later. Now, I request Dr. Rajiv Dhar, General Manager Subsurface of SR. Rajiv Dhar is basically a geologist, and he has been working at a very senior position in SR, and we had a great association with him while working on this multi-component data under the CSIR project, and he has really extended all the possible help from SR. So Rajiv, you can load your presentation. He's going to talk on the structural control on CBM well production. So we really hope that some interesting findings we'll have from your presentations. So I'm sure audience are aware that SR is kind of the leader in CBM production in this region, and they in the panel discussion we have their vice president also. So we are hoping to have a great discussion with them in the panel discussion. Voice is not very clear. Even slide is not visible, Rajiv.
Okay.
Yeah, your slide is visible, Rajiv, but voice is not very clear. It's like breaking. But you can go ahead. We'll see. Yeah. No, voice is not clear.
Am I audible now?
Yeah, perfect.
Okay, that's fine. So thanks for giving the opportunity. So I'll try to restrict my presentation within the limited time. So basically, I will start with the this general understanding as Dr. Mollik and you also mentioned. So the moment we talk about the whole bed methane, so we talk about the two parameters only, the permeability and the adsorbed gas. So if this is the thing, and then if you have permeability and if you have the gas content, then you should have a good result always. At the same time, if you talk about the any CBM field in US, Australia, in India, I believe that 20 to 30% of the total drilled wells are actually contributes 80 to 90% of the total production. So in general, in India, rather we all CBM industry have a general idea. Okay, gold being a just weighted deposit. So if you have the gas content and if you have the thickness, you have the resource, so you have the success. But actually, there are some other major factors which is controlling the whole thing. Probably the structure is the one of the major concern, major controlling factor. What we used to say, this 20 to 30% of the total well is actually producing 80 to 90% of the total production. So I'll go through just few examples from the Black Warrior Basin. That is the two basin we are talking about, Oak and Grove, and it is from the some published literature by Pashi. So as you can see that this, my cursor is visible, I believe. So these big bubbles is actually the higher gas production in the structure closer area. So this is for, and again for the fault region, if we talk about, so mostly we can see that this is the left one is the peak gas production. The bigger the bubble, the bigger the rate, and the right one is the peak water production. Again, the bigger the bubble, the bigger the rate. So if we talk about, then we can see that mostly in this half graben structure, the upfront part have a better gas production than that of in the downfall side. So either in case of compressional field, that is in the fold and all this thing, or in case of tensional field, that is with the normal faults and all this thing, basically structure is playing one of the major role. And as Dr. Mollik was also saying, basically this is somehow related to the secondary fracture generation and permeability enhancement. In addition to that, some other pressure mechanism also is working at the stage of deworking. So it is a conceptual model by Peshin et al. Itself. So as we can see that in the top one, that is when we are in the extension field, the moment we are near to the rollover anticlines, my gas production is actually increasing. And as we know that always this rollover anticlines or normal anticlines, the place portion are always with some extension thing and some fracture, secondary fracture generation and permeability, all these things are better. Similarly, for the compressional field, again, near the this detachment folding, again in the hinge part, this is gas production is always better. So coming to some of the example from Ranigan field itself, so I have taken a three cross section. That is one. This one, the left corner is A dash cross section, which is basically a anticlinal structure formed because of the drag of the normal fault. So what we have observed that the wells situated in the hinge part of the anticline are always with a very good gas production that is in the range of 20 to 25,000 cubic meter per day. And the moment you are coming to the lean, actually your water production rate increased and gas production comparatively decreased. So now if we think that, okay, so if you stop the dewatering and if you go for the only dewatering in the hinge part, probably we'll lose the game. Basically, in case of this continuous system, the downward side wells are actually helping the upward side wells situated in the hinge part. Now coming to again the another section, that is B dash. So here basically multiple normal faults with throw in the range of 30 to 50 meter and somehow going to 100 meter even. So here also we observe that with this type of minor faults, that is having throw of 20 to 50 meter and associated fractures, yes, of course, some of the wells you have the fault pattern, etc., but your permeability is increased. So within the fault zone itself, and particularly in the upstream side, the production of gas and water both are in the higher side. And when as you go away from this multiple small fault zone and in the downzone side, basically your production get little bit decreased. Another section in the same almost same area, that is C dash, which is showing me that particularly when we are coming to a big fault having a throw 350 meter or 400 meter in the range, so near the fault basically your production decreases drastically, and as you move away from the fault almost in the homoclinal sequence, that is you are getting a better production. So basically all these things with the present practice in the CBM industry, without having the seismic data and this thing, so we come up with the model with the based on the well correlation and all these things, and that's become always a challenge for the structural disposition. So even today, I understand that today we have even maybe you are not very much equipped to map the 1 meter coal seam or something, but for the going for with the exploration first, if we have the structural control based on the seismic data, so that will actually reduce the cost drastically, because if not those 20 to 30% well, maybe you we can reduce the number of wells drastically, which will actually reduce the development cost. And here the seismic comes into the picture in a bigger way for the CBM industry. And particularly if you talk about again, say our friends and colleagues of working in US and Australia, normally if they don't have even the 3D seismic for the structural control, at least they have the 2D seismic, and accordingly they're going forward. So that part is missing in a little bit in case of Indian CBM scenario. And for that, actually, we are again collaborating with the this, CSI institutes and etc. And I think way forward, uh, it will be a good thing. And with the model that Dr. Maulik was showing, so that is also very interesting. So if you can map the permeability, it will be a really good thing based on the seismic. So that's all from my side. Thank you.
Thank you, Raju, and special thanks for such a quick and wonderful presentation. So I hope that you will also have some queries, especially from seismic people also. So we'll discuss them later. So now I request Pankaj Kumar from Immersion to load his presentation. So Pankaj, we are collaborating